Modern time series forecasting is dominated by massive models. Informer transformers process data through dense, multi-layered architectures, using complex attention mechanisms to map relationships across time. Yet on long-horizon forecasting benchmarks in 2022, these computationally heavy models were beaten by an aggressively simple alternative called DLinear. DLinear strips away attention mechanisms entirely. It relies on a strictly linear approach, reducing the architecture down to a minimalist block diagram. The core operation powering this model is a single highly studied algorithm, the moving average. The moving average is the foundation of a 120-year-old mathematical lineage built to solve one structural question: how exactly do we weight the past? This visualization shows the core function of DLinear's decomposition block. It takes a raw, volatile time series and splits it into two distinct physical components: a smooth moving average trend line and a jagged, oscillating remainder line. Once separated, DLinear fits one independent linear map directly to this smooth trend component. It then fits a second, entirely separate linear map to the remainder component, which captures the repeating seasonality. This extraction process is mathematically basic, yet it produces a signal clean enough to outperform modern deep learning. We need to define exactly what properties make it so robust. To understand DLinear's effectiveness, we have to reverse engineer its decomposition block back to the physical constraints of 1930s economic theory and 1900s actuarial science. Data smoothing originated with 1900s actuaries. They stabilized insurance premiums by replacing jagged death rates with locally averaged values, a process called graduating the tables. Mathematically, this is the centered simple moving average. It takes a single data point and replaces it with the equal average of its immediate neighbors in time. By 1931, economist Frederick Macaulay formalized this process for economic series. We can test his methods using the classic air passengers monthly dataset. Plotting the raw passenger data, increasing the window span from a 3-month to a 7-month, and finally a 13-month average progressively flattens the seasonal sawtooth. A 13-month span perfectly averages a 12-month cycle, creating a frequency null that annihilates seasonality, leaving pure trend. But a centered average has a critical flaw for live forecasting. It requires knowing future data points to calculate the present. For real-time operational models, engineers must use trailing averages, which only look backward. Forcing the equation to look only at past data introduces the central penalty of all real-time filters: massive phase delay. A trailing simple moving average will always settle behind the current trend. Specifically, it lags by exactly k-1 divided by 2 steps. Tracking a raw dataset with a sudden step-level shift at time 100 reveals how long a trailing filter takes to catch up. The equal weight SMA reacts sluggishly. Because 9-day-old data carries the exact same voting power as today's, the filter's memory drags it down. To fix this, actuaries introduced the weighted moving average. By distributing the weights unequally, they could shift the filter's center of mass forward. When we apply linear weights, giving recent observations the majority of the vote, the filter reaches the new baseline significantly faster. Weighting recent data heavily minimizes phase delay. But executing these unequal weight calculations across thousands of variables hit a hard physical wall against mid-20th century hardware limits. In 1956, Robert G. Brown was tasked with predicting inventory demand for the U.S. Navy. He needed to track thousands of distinct, heavily demanded items. Running long, weighted moving averages for every single piece of inventory was mathematically ideal, but computationally impossible on the era's punch card machines. Brown engineered an elegant solution. Instead of fixed spans, he let voting weights decay geometrically, controlled by a single parameter, alpha. This chart contrasts an alpha of 0.1, remembering past data longer, against an alpha of 0.5, forgetting rapidly. A high alpha tightly hugs volatile data, while a low alpha smooths the curve at the cost of heavy lag. This formula, the exponential moving average, is mathematically infinite. Yet it updates by storing only one single number from the past step and executing exactly one multiplication. This structural frugality allowed complex statistical forecasting to run on 1950s punch cards. But the exponential moving average has a strict mathematical failure state. It breaks down completely when applied to data with a persistent directional trend. This graph demonstrates a clean upward trend. When a single EMA is applied, it settles into a fixed trajectory, permanently locked below the true signal. This vertical gap is a predictable mathematical artifact. The filter lags the trend predictably. Brown repaired this by smoothing the already smoothed series. Double exponential smoothing measures the distance between the two calculations and adds it back, perfectly closing the gap. Charles Holt and Peter Winters soon expanded this logic, adding a third recursion specifically for seasonality. This created the Holt-Winters ETS state space models that remain default operational baselines today. Every historical innovation in time series filters is simply a targeted mathematical patch for a specific bug in how past votes decay. All of these methods exist under one absolute physical boundary of filter engineering. There is no free filter. Noise suppression is always bought with delay. This scatter plot maps out the empirical trade-off frontier. We measure the smoothness of the line on the vertical axis against the phase delay on the horizontal axis as the filter window grows. Small window increases yield massive wins, gaining steep drops in noise suppression with minimal lag penalty. But the curve eventually flatlines. Increasing the window size further yields almost zero extra smoothness, while the lag penalty climbs endlessly toward a critical failure point. This defines the ultimate engineering rule. Choose small lag for anomaly detection and live forecasting decisions, but tolerate large lag for clear aesthetic presentation. Pushing too far along this flat line triggers the Slutsky effect. Excessive smoothing delays existing cycles and begins mathematically manufacturing false ones out of pure noise. Navigating the exact physics of this trade-off curve is the core task of any forecasting architecture, from a 1900s actuary to a modern deep learning engineer. Which brings us back to the 2022 DLinear architecture that embarrassed modern transformers. Returning to DLinear's moving average block, we can now see it for what it is, a perfect, modern distillation of Macaulay's 1931 workflow. It smooths the series to find the pure trend and splits out the remainder. DLinear completely sidesteps the deep learning trap of over-parameterization. It applies simple linear regressions strictly to these isolated, mathematically clean components. Dense transformers struggled on long horizons because they attempted to learn temporal dynamics entirely from scratch. DLinear succeeded because it hard-coded the foundational physics of time series directly into its architecture. When a linear model outforecasts a transformer today, it is not an anomaly. It is the actuarial graduation lineage, seamlessly caching a 120-year-old mathematical check.